So once we've done some stuff with calculus, we want to start using it in an algebraic way. And that's where differential equations come in. Differential equations are what they sound like, although they sound weird now, but the differential is that dy or dx. That's the differential of y and the differential of x, the derivative, basically. A differential equation is an equation where the variable that you are working with is a differential. So the derivative is part of the equation. To solve that, that was weird, but anyway, to solve something like that, you would isolate, resolve, and solve. That exact same method we've been using since Algebra 2 with functions. Get it by itself on one side of the equation, get rid of it by using the inverse, and solve whatever's left over. So that's what we're going to do. Now, we're going to look at the very, very, very basic form where isolation can be done. So for this first exercise, which is identifying separable equations, it wants to know, can this differential equation be solved using separation of variables? Which means, are you able to get all of the, let's say, x variables on one side of the equation, all of the y variables on the other side? Can you separate the variables? And in this case, yes. We start out with dy over dx is equal to cosine x over 3y minus y squared. Can I get everything that has a y in it on one side of the equation and everything that has an x in it on the other side of the equation? Yes. I'm going to multiply by dx. And I'm going to multiply this by 3y minus y squared. So that what I end up with is 3y minus y squared dy is equal to the cosine of x dx. So I have separated the variables. So the answer is yes. We could solve this by separation of variables because it is possible to separate the variables. In fact, you can probably figure out this is the isolate part of the problem. Our next part would be to integrate both of those, which would get rid of the dy and the dx, and then we would solve for y in this particular case. So yes, it is. You can do this by separating the variables. This one. Could we solve this using separation of variables? Well, this one's not as straightforward as the other one, but I think it might be doable. But we have to use some algebra. dy over dx is equal to e to the y plus x. So e to the x plus y, excuse me. Doesn't really matter the order, but we'll do it their way. E to the x plus y. So in this form, no, it's not. Because there's no real way to get that y over here. But e to the x plus y, that exponential form, can be broken down a little bit because if we have addition in an exponent, I can write that as multiplication. So this could just be e to the x times e to the y. And if that's the case, then I can divide this over and multiply. So what I end up with is 1 over e to the y dy is equal to e to the x dx. So yeah, we can solve this by separating the variables because it is possible to separate the variables. Yes. I'm assuming they have some in here that are not possible. This one. Now, you may think on this one that yes, that is super easy to do. We just add 3 cosine y to both sides and we're good to go. But it's not. If I add 3 cosine y to both sides, what I end up with is dy over dx plus 3 cosine of y is equal to 2 sine x. Okay. But I can't get rid of this dx because now if I try to multiply both sides by dx, I get 3 cosine y dx. dy plus 3 cosine y dx equals 2 sine x dx. It doesn't work. There's no real way to untangle these. No matter what we do, we're not going to be able to get an expression of dy and an expression of x dx. It's not going to work. In fact, this addition is a problem too because this is dy, so the integral would work. But this, when we try to integrate this side, isn't going to work at all. In this case, no. There's just no way we can actually separate. This would be that no case there. Okay, good. Now, actually doing separable differential equations. So here we want to solve the equation. It is negative e to the x over 8. Okay. So we have dy over dx is equal to negative e to the x over 8. Now, this one we don't actually have to do anything separable, really. We just solve it, integrate both sides. But I'm gonna multiply that dx over there. So we get 1 dy is equal to negative 1/8 e to the x dx. So I separated the differentials. I had dy over dx, which is y prime, and I just separated it out so I have dy dx. Then, since we've separated the variables, since we've isolated the variables on one side of the equation, now, to resolve the differential equation, I integrate on both sides. Here, the integral of 1 dy is y, because we are integrating with respect to y on the left-hand side of this equation. The integral of negative 1/8 e to the x dx is negative 1/8 e to the x. Doesn't change. That's negative 1/8 e to the x. Now this one comes out solved for y, and that's because we didn't have any y variables, we just had x. So we could have just integrated initially, but that's how all of these are really going to work, plus c, which we could then solve for if we knew an initial point. But we just find out, which is this one here, b. So that's not a great example. Not as fun as they can get. Let's see if the next one's a little better. There we go. All right. So dy over dx is equal to 3 over xy squared. So notice, not only do we have y, but we have the derivative of y. Not only do we have x, but we have the derivative of x in the equation. This is a differential equation. And we're going to solve it by separating the variables on two sides, one on the left, one on the right, and then integrating with respect to that variable. So separating out, I'm going to multiply both sides by y squared so that I get y squared dy And then I'm going to multiply the dx over here, so I have 3 over x dx. Yeah. So simple algebra, moving terms around, separating them out, so that now I have this. You can even imagine if you want that nice integral form, put a parentheses around your variable and your dy dx. So that my next step is to integrate both of those sides. Left side with respect to y, so we're going to add 1, divide, so we would get y to the 3rd power over 3. And then on the right-hand side, 3 over x is 3 times the natural log of the absolute value of x plus c. There's technically a plus c from each of these integrals, but since we could just subtract the constant over to the right-hand side, we can represent all of the added or subtracted constants in that 1 plus c, so we're not worrying about it here. But now, you'll notice all your answer choices are solved for y. That's going to be our next step, solve for y. So we need to multiply by 3. So y to the 3rd is equal to 9 times the natural log of the absolute value of x. And 3 times a constant is still a constant. So we just need that plus c still. It does not change. Its value changes, but we don't know what its value is, so it's still going to be represented by plus c. And then we take that cube root. So y is equal to the cube root of the entire side. So 9 times the natural log of the absolute value of x plus c. That's what we're looking for in our answer choices. So we look, that's not it. That's not it. Can't see the rest. We're going to have to scroll down. This one is good. This one is not. They changed that absolute value, so we're going to go with C. C is my answer choice. That's exactly how it works. Separate the variables. And work it down. All right, guys. That's the end of calculus. Besides the tests and the work, but that's the last video, or this is the last video that I'm going to post. I want to say, for a lot of you, it's been a pleasure teaching you. For my seniors, I wish you the best of luck in your future endeavors. I really wish we had one last chance to say goodbye in class, but that would be dangerous. For my juniors, hopefully I get to see you next year a little bit. Fill me in on how you're doing. But otherwise, again, it's been a pleasure teaching you. I'll miss you. Good luck, guys. Stay safe.